start that. We are doing our last new material today, and that is section 11.2. Which is tests for independence, which also means the same thing as tests for association, between two categorical variables. Now, do you remember back in chapter 3? No, that was like 6 months ago. But chapter 3 was association between two variables. And we first learned how to deal with contingency tables. Remember that? Okay? And at the time, I even had a test question. Is there evidence of association between these variables from this contingency table? And all we had at the time was what we call the eyeball test. You just look at the numbers and go, ooh, yeah, they're really different, or they're about the same. And I promised you at the time that later in the semester, we'll have a hypothesis test for this, and today's that day. I'll save it for the very end. And it is known as the chi-square test for independence. I'll repeat it. Chi-square test for independence. Or some books, including this one, at some places will say test for association instead of test for independence. But that means the same thing. It's like one of them is the null hypothesis, the other one is the alternative hypothesis. The null hypothesis is the two variables are independent, and the alternative is the two variables are associated. So you can test the null or you can test the alternative. I don't care which of those words you use. So test for association. This is spelled out like this. The chi-square test. Okay? So those of you that are in class today, and it looks like pretty much everybody, but if somebody wasn't here, and I can see a couple people that are missing, when they come back on Wednesday and they say, hey, can you please explain to me what the chi-square test is? Then you can snicker. It's pronounced chi, because you were here to hear the pronunciation, right? It's pronounced chi, but a lot of people mispronounce it as chi square or chi square, but it's the Greek letter chi, like you see on the sides of sorority buildings, right? So a capital chi is just a big X, but this is the lowercase chi, and I'm not real good at drawing it, and neither is the calculator. So when we do it on our calculator, it kind of looks like an X, but it looks distorted. Well, that's the chi-square. Okay? So, I've already hinted that our calculator is going to do this for you, but we're going to go through how the test is done, because I think it's important that you understand that, how the test is actually computed, what the calculator is doing. But the nuts and bolts, the grunt work of doing the calculation will be done by the calculator. Okay? So, what I'm going to do is I'm going to pull up some contingency table data from the very first time we hit contingency tables, and we also showed this exact data just last class period when we were talking about adjusting for variables. Well, that's not very big, is it? I need to make it a slideshow in order to make it bigger, I guess. There. Oh, and now it's up on the screen. Let me play with this just a little bit. If I make that big, and then if I scroll. Can I get the numbers? Yeah, almost. There, are those big enough to see? My my no and yes ended up on here, but you can see them, right? I want to be able to write on them, so I don't want to have to pull the screen down. So this is smoking, no and yes. And then this is exercise, no and yes. So I'll put no and yes for exercise there. Okay? Now this is the exact data that I showed back in chapter 3. In fact, the name of this file is chapter 3, section 1, PowerPoint presentation. So this is the data that we saw back then, and we said, does this data show evidence of association? And do you remember what your answer was? Yes, very strong evidence of association. And what did we compute in order to do that? We don't just look at the raw numbers, we computed something. What do you compute off of there? Proportions. And we call them conditional proportions. Very good. So conditional proportions. So the next slide adds those conditional proportions. Oh, I messed up where my no and yes were. Okay? So here are the conditional proportions. So just looking at those two numbers, what does the eyeball test tell us? There's very strong difference. If there was no difference, if the null hypothesis were true, what would you expect those two numbers to be? The same, right? They would be equal to each other. There would be no difference. In fact, this is P1 hat, this is P2 hat from a two-sample proportions test. So in the very special case of a 2x2 table, 2 rows, 2 columns, that test can be done with a 2-prop z test. So we already have done a test like this. We did it last time. Remember when we were deciding if we needed to adjust for exercise, we tested this very data to see if there was a significant relationship. So over here, I'm going to summarize those results. The 2-prop z test, the null hypothesis is P1 minus P2 equals 0. And the p-value from that test, do you remember what it was? You're supposed to memorize numbers when we get them in class.
0.001.
Yeah, that's right. Let's get it really accurately out to a whole bunch of decimal places. So go ahead and do it on your calculator. Do a 2-prop z test on that data. And if you have any hesitation at all on, oh, what numbers do I plug in, then you know you need to do some studying before the final, right? Because there will be 2-prop z tests on the final. And while you're doing that, I'm going to pull up the, I guess I can't because I have to close this to pull up the TI-84 simulator. And you're looking at the numbers. Does anybody not know how to do that? What?
Is this a two-tailed test?
Yes, please do a 2-tailed test. Jordy?
Okay, so the numbers we put in, x1 and x1 is 217, and then n1 is 322, right?
Perfect.
Okay, I have it done.
Okay, this is x1, n1, x2, n2. Okay, and so you have the p-value?
Yeah, it's 1.046 times 10 to the negative 7.
Okay, go ahead and give me about 2 more decimals.
Oh, okay, so
592.
yeah,
Instead of the 6.
592.
592 times 10 to the what?
Negative 7.
Negative 7. Okay. There's a reason I want that many decimal places, because I'm going to compare it to the p-value we're going to get out of this chi-square test in a second. And you'll see you get the same p-value. Now, what is the p-value again? I keep forgetting that.
Probability of getting results like we got, or further from the null if the null is true.
Probability of getting results like we got or even further away from the null? Well, the null says there's no difference between the two proportions, and we got proportions that were really different. 67% versus 31%. That's really different. So if the null were true and in the population there's really no difference, how likely is it you could draw a sample of 385 people and get 67 versus 31? That's the probability of that. In other words, it ain't happening. You're actually more likely to win the Powerball lottery than that. Well, actually, it's about the same. It's about 10 to the minus 7, which means it's not going to happen. Sorry to tell you that. So that's one way of testing. That only works in a 2x2 table. Suppose I had a contingency table that was a 2x3 table. Then which two proportions would I compare? Well, what if this was 20%, 20%, and then this one was 70%, and this was 10%, and this was 10%, and this is 70%. Then clearly these two are different, right? If this were smokers and non-smokers, they're very different, but if you just test those two proportions, you'd say, oh, they're the same. So a 2 prop Z won't work if you got more than 2 props to compare. Now wait a minute, I always get this question right here. Wait a minute, don't you have 4 proportions in this table? Yeah, but what? If I know this proportion, then I know this one by default. So this column is redundant information. If you tell me how many there are, and then how many successes there are, I can tell you how many failures there are. But down here, just because I know that column doesn't mean I know this one. So I need 2 of the columns, and then the third one is redundant information, right? So you can't do a 2 prop Z. So we need to extend the 2 prop Z into tables that are bigger than 2 by 2. And that's what the chi-square test does. Okay? So here's the way that chi-square test works. First of all, the null hypothesis. For a chi-square test, the null hypothesis is there is no association between smoking, and then in parentheses, to make it general, I'm going to say that's my row variable, and exercise, and that's my column variable. Okay, so can you read that? There is no association between smoking, which is the row variable, and exercise, which is the column variable. That's the null hypothesis. So what's the alternative hypothesis? There is association. And all chi-square tests are set up that way. The null hypothesis is no association. The alternative is there is association. But I want you to write it out in context, which means don't just say between the row variable and the column variable. Say what those variables are. Okay? There's no association between smoking and exercise for this particular problem. Okay? We're used to having null hypotheses written out like this, with symbols and mathematical equations. But for a chi-square test, there's really no way to do that in general, because there isn't a 3 prop or a 4 prop Z test. Right? So you could say, I guess you could say, no, you can't. There's really no way to set it up with P's. It is proportions you're comparing, but there's no way to set it up and say, well, this one's equal to this one, and then this one's equal to this one, and then this one across the columns. It just doesn't work. So we just say, well, I don't know how to do it, so I'm going to write it out in words. There is no association, or there is an association. Okay? So, like all good hypothesis tests, good or bad, all hypothesis tests, the way that you test the hypothesis once you have data is to do what? You collect some data and you see if, okay, you see if the data supports your alternative hypothesis, right? And it either does or it fails to. Well, how are we going to do that?
Our calculator?
Yeah, that's right, our calculator. What we always do in a hypothesis test is we set up a hypothesis, a null hypothesis, and then we see how well our data matches to that. Well, it's kind of hard to figure out, well, how do I do that when I don't have symbols and numbers to match to? Like if I have a 2-sample t-test, then I have mu1 equal mu2, and then I can look and see if my sample data, x bar 1 and x bar 2, are equal, or close to equal, and then that matches up. But here, how do I do it? Well, I want you to figure that out. So what I want you to do is I want you to fill in these circles with numbers that would make the null hypothesis true. Remember, p-values are always computed. If the null were true, well, if the null were true, what would you expect to get in these cells? Now, the only restriction I'm going to give you is that you have to have 385 people. And you have to have 322 non-smokers and 63 smokers. Okay? But I want you to change the numbers. 217 and 20, instead of those numbers, put other numbers that make the null hypothesis true. What would that table look like? Well, as a little hint, most people just kind of stare blankly for about 15 minutes when I do this. But to give you a little bit of a hint, we decided there was strong evidence in this table because this percent was very different than this percent. If the null were true, what would those percents look like? They'd be the same.
So you want us to change the percents?
I want you to change the numbers so that the percents are the same.
Okay, what would the limitation? There has to be 63 and 322 in each one.
Right. You have to make this number and this number add to 322. You have to make this number and this number add to 63. Okay? Get busy. I will pause the video while you guys are doing that so they don't have to stare blankly. Okay, so if 50% doesn't work in each of those, what percent do we want to make them both equal to? I want this percent to match this percent. That would make the null hypothesis true. Right? What's the overall percentage of exercisers? If smoking doesn't affect the percent who exercise, then the percent of exercise in each of those two groups should be the same as the overall percent of exercising. Ah. So what is that overall percent? And that's what the calculator, when we do the 2-prop z-test, if you paid attention, it gave you a p-hat with no subscript. And remember, that's the pooled estimate. Which is x1 plus x2 over n1 plus n2. So this is x1, x2, n1, n2. Well, that's this. This is x1 plus x2. This is n1 plus n2. So if you take 237 and divide by 385, what proportion do you get?
61.56.
6156 as a proportion. Okay, that's what proportion I want you to make both of those.
I figured that out, actually.
You got that?
I got that number somehow, but.
Okay? So now, how many of the 322 have to go in here in order to make it 61.5%? How do you do that? I want to know what is 61.56% of 322. You times it. So do that. Take 0.6156 times 322. $198.22. We'll go to 2 decimal places. Okay. Now you should be able to confirm pretty quickly that if I put 198.22 in there, that my conditional proportion of exercisers in this group is 198.22 over 322, which would be 61.56. Now do the same thing for the smokers.
123.78.
120.
Oh wait, never mind. That's the opposite of the other one.
Oh, that goes over
yeah,
here?
That one goes there.
Okay, and how'd you get that?
Subtracted 198.22 from 322.
Good. And I wanted to make that point. Once you get one number in a row, you can get the other number by subtraction. But you could also do the same thing and get the proportion 148 over 385 and apply it to the row total of 322, and you can get that same number. What about this number?
38.78.
38.78. Okay? Now, confirm for me that those two add up to 237, which is the requirement I gave you.
They do.
Woohoo! They do. Okay? Now what about this number? It's the only one we're missing.
24.22.
24.22. And how'd you get that?
Just subtracted the 38 from the 63.
Good. Subtracted 38.78 from 63 to get what's left over. Right? And in fact, if you add all 4 of those numbers together, you should get 385. Yeah.
So we just basically had to find one number, right?
Good point. Once I knew the 198.22, I could fill in the rest of the table by subtraction. That is known as its degrees of freedom. This table has 1 degree of freedom. And all that means is, how many of the cells do I have to know before I can get all the rest of them by subtraction? So what if I had, that was for a 2 by 2 table. What if I had a 2 by 3 table?
2.
Well, think of it this way. If I had a 2 by 3 table, if I fill in that cell right there, can I get any other cells by subtraction?
Yeah.
Yeah, which one? The one below it, right? Can I get any more? No. Okay, so if I fill in that one, now I can get this one,
And you get the last 2.
and I can get this one by adding that way, and I can get this one now because I have that. So I fill in 2 cells, and I can get the whole table. So this one has degree of freedom equal 2. What if I have a 4 by 4? Not 3, not 4. How am I getting it? We got to come up with a formula. Well, basically, look what happens. You mark out 1 row and 1 column, and however many cells are left. All right, mark out 1 row and 1 column. So if I have a 4 by 4,
6.
mark out 1, and I'm left with how many?
9.
9.
Oh.
So it's this. Degrees of freedom are equal to the number of rows minus 1 times the number of columns minus 1. R minus 1 times C minus 1. Take out 1 row, take out one column, and multiply the size of the rectangle that's left, and you get your degrees of freedom. Okay? So that's degrees of freedom. Now, guess I'll get rid of that for now. I want you to look at how we got these numbers. What did we actually multiply together to get 198.22? Well, the first thing we did was we got this 6156, right? And then I multiplied that by 322. So what I did was I took 237 over 385 times 322. And that's the column total times the row total divided by, what's 385?
The whole total?
The total, or we call that the grand total. And that formula for expected counts works for every cell in the table. Like for this 123.78, my column total is 148, my row total is 322, my grand total is 385. If I take 148 times 322 and divide by 385, you'll get 123.78. Okay? Yeah, that's cool, isn't it? I thought you would agree. Okay, now let's get back to the hypothesis test. Remember how hypothesis tests work? You compare the observed data to the data that you would expect to get if the null were true. Well, that's what these numbers are. These are the numbers you would expect to get if the null were true. I would expect to get 198 in this cell, but I got 217. Way more than expected. In this cell, I'd expect to get 30, almost 39, and I only got 20. Way less than expected, right? So you need to do some comparison cell by cell. This cell's way bigger than expected, this one's smaller than expected, and here's how that's done. The chi-square test statistic is just marked as a chi-square, and it's equal to the sum across all cells in the table of the observed counts minus the expected counts squared, to get rid of negatives, divided by expected counts. Since we're not dealing with proportions here, we're dealing with counts. We don't have a standard error to divide by like we're used to. So we standardize by the expected count. So it's just observed minus expected, quantity squared, divided by expected in all of the cells, and then add them up. Okay? Now I'm not going to go through that entire calculation, but I'll do the first couple of terms so you can see how this is done. But your calculator is going to compute this for you automatically. Here we go. Let's start at the upper left of the table. My parentheses would have what in it? Observed is what? Upper left of the table? 105.
Oh.
Minus the expected in that cell.
322. Oh.
123.78. Quantity squared divided by the expected count, which is 123.78. Then you're going to add to that the next cell. This is the upper left. Now let's go upper right. That would be 217 minus 198.22 quantity squared over 198.22. Then you're going to add lower left plus and lower right. And I'm not going to bother to write those out, but that's how you would get the test statistic if you had to compute it by hand. First you find the expected counts, then you measure the difference between observed and expected, standardize them, and add them up. That's a lot of work. And it is a lot of work, which is why we have you buy these fancy schmancy calculators. Right? So you ready to learn how to do it on your calculator? Thought you might be at this point. So what I'm going to do is I'm going to pull up my calculator simulator, but I want you to do it on your calculator with me so that you know how to do it. And I had to remove the table, so I'm going to fill back in what those observed counts were. And I'm going from memory here, so correct me. Is that correct? Okay, so those were the observed counts, and underneath them are the expected counts in those cells. Okay? So here's how it's going to work. A contingency table is like a matrix. You know what a matrix is? Okay? The calculator will deal with matrices. So push the second function button, and then see the word matrix right here where I'm wiggling the cursor. It's above the button that has x to the -1 power on it. So click that button, and you should get this menu. It says Names, Math, and Edit. Go over to Edit. Most common mistake here is to stay in the Names mode, and then people can't figure, well, my calculator's not working right. The first thing where the cursor is blinking now are the dimensions of your matrix, or of your contingency table. And it goes rows, then columns. So in this one it's square, so it's 2 by 2. But it's always rows first, then columns. Okay? So change it to 2 by 2. It probably defaults to 1 by 1 when the first time you ever use it. But change it to 2 by 2, and then it'll give you space in the matrix to enter the 4 numbers. So type in the number, press enter. The cursor will jump to the next place. Look to where it jumped so you know what number to enter, and get all 4 numbers in there. And it should look like mine when you get done. Okay? And I forgot to mention, but when you go into that, when you first go into matrix and you have the 3 words across the top, you go over to edit, always work with matrix A. There's a whole bunch of them. There's A, B, C, D, on down. Just don't ever use any of them but A. And then you don't have to figure out how to change when you go into the chi-square test to tell it I'm in a different matrix, because it defaults to A. And it's kind of tricky figuring out the sequence of button pushes to change it to some other matrix. So just leave it at A. Always work with A. You'll never have a case in this class where you need more than one of them. Okay, everybody have the matrix in now? Okay, so you're done with this screen, you're ready to go to the test. So like all of our tests, we start by pushing the stat button. So you push stat, arrow over to tests, and arrow down, although you can get there faster by going up, to the chi-square test. Which, like I said earlier, oh man, I hit the wrong button. Now I got to go through the whole thing again. The chi-square symbol doesn't look real great, but that's it. It's like a stretched X, kind of. And there's 2 of them that have that. The first one is the chi-square test. That's the one we want. The next one says GOF, and that stands for goodness of fit. That's the chi-square goodness of fit test, which is in section 11.1, which we skipped. We're in 11.2. Right? So If you ever want to go back and do that one just for fun, like over Christmas break, then there's the test you'll use to get it. All right, so chi-square test, hit enter and select that. And it says observed. And observed says what matrix did you put the observed counts in. Okay? And like I said, always put them in A, then you don't have to change this. And then expected matrix B. And I know you're thinking, wait, I didn't put my expected counts into matrix B. I better go back and do that. And that's what I thought for the first couple of years that I taught this class using this calculator. And finally, a student said to me, you know, you don't have to enter them in there. It puts them into matrix B. So it's just telling you here, it's asking you what matrix do you want me, the calculator, to put the expected counts into. So I was always typing them in, and then it would overwrite it, and I'd never know the difference. See? We can't all be smart. So once you get to this screen, if you put things in matrix A, you shouldn't have to change anything here. Just hit calculate. So go down and hit calculate. Mariana?
What if the calculator doesn't say matrix A for observed?
Uh-oh. What does it say?
Well, it said B, but then I cleared it.
Okay, what you'll have to do is put your cursor in that spot and then go into matrix and then select names, arrow down to the one you want, and press enter, and it'll put that matrix there.
Okay, got it.
So it's a little tricky. Okay, so you hit calculate and you get a test statistic of 28.21. So that's what this would have been if we'd have finished it out. 28.29. And a p-value, I guess I'll write it down here. A p-value of 1.0437 times 10 to the negative 7. Okay, does that look familiar? It's not quite exactly the same as this one, but it's close. And the reason that it's not quite exactly the same is because the calculator does round off these expected counts. I'm not sure how many decimal places it keeps. It only shows you 2 of them. When we go back and look at matrix B, you'll only see 2 decimal places, and it may use only 2, but I'm not sure how many it uses, but it doesn't use an infinite number, so it's not going to match quite exactly, whereas the 2-prop Z test is using exact counts. Okay, so now we have a p-value. What's the conclusion of this test? Reject the null. The null says there is no association. We're going to reject that. And we're going to say we have sufficient evidence to say there is an association between smoking and exercise, which is exactly the same conclusion that we had before. Same conclusion from the 2-prop Z test, obviously.
So why did we do it this way?
Good question. You were reading my mind, because I was going to say, so why do I need the chi-square test? Well, I don't need it if I have 2 by 2 tables, but I do need it if I get bigger tables, like this one. Well, I got so much clutter on here, can't read the table. Remember this data? This is smoking again. So this is no and yes for smoking, and then this is health rating. Is there an association between whether or not somebody smokes and how they rate their health? And we did this one back then too, but again it was only the eyeball test. But I can't do a 2-prop Z test this time because I got too many cells. Right? So do the chi-square test for this one. Now, stop for a second. I forgot. There's 5 steps to every hypothesis test, right? What's the first step? Check assumptions. And I haven't talked about that yet. So what are the assumptions for a chi-square test? Well, the first one is random samples. Right? You're used to that. Random samples. There's a ghost in here. So assumption number one are random samples. Assumption number two there is at least, that's not how I want to say that. Let me start it over. The expected counts in all cells of the table are at least 5. Remember the 15 successes, 15 failures thing? This is that same thing, only when you have 4 of them you're looking at instead of just 2, then you get to come down off that 15. You don't need quite as many. So basically it's saying I need at least 5 successes or failures in every single cell of the table. So all the expected counts have to be at least 5. Well, what about these 2 cells?
No.
We're not going to hit it here because I only have 1 that I have to distribute. There's no way I'm going to get 5 in both of those cells when I do expected counts. So what I'm going to do is I'm going to combine the 1 and the 2 together. Let's make a new column of 1s and 2s. So this is going to be 13 and this is going to be 9 for a total of 22. Okay?
What about the last column?
The last column, we'll have to find out if that one's going to work or not. The observed count is 1, which is not enough. But it's the expected counts that have to be 5. And how do I find the expected counts? Well, the easiest is to do the chi-square test and then go look at matrix B. So let's do that real quick. We know this one won't work, so I'm going to replace with 13 and 9. So now I have, what are my dimensions of this matrix?
2 by 4.
It's 2 by 4. So go into your matrix, tell it it's 2 by 4. And I can't do it for you up here at the same time because then I'll be hiding the data from you. But let me make these a little bit bigger for the video. There are the numbers. We don't really need the row and column totals because we're letting the calculator do the work for us. But actually, now that I have the numbers, I could pull up my calculator.
So is this considered a 4 by 4?
No, it's a 2 by 4. There's 2 rows and 4 columns.
Okay. All right.
Okay? So let me go ahead and pull up the calculator. Well, I don't have time. We only got about 1 minute left, so you're just going to have to do it for me. What did you get for a chi-square test statistic?
39.434.
Okay? So chi-square is 39 point what?
434.
434. Now that number, usually we say, well, that's the number of standard errors, but it doesn't work that way with chi-square. So that number just doesn't mean anything to me. All I really care about is the p-value. So what's the p-value?
1.40 times 10 to the negative 8.
10 to the negative 8. So is there an association?
Yeah.
Yes. We have strong evidence that there is an association. We're going to reject the null hypothesis. Okay. Now, before you go, check your matrix B. Go back to second function matrix, go over to edit, and go down to B and press enter, and you'll get to see what's in matrix B. Then look to see that all of them are at least 5. If they're all at least 5, then you can trust this chi-square result. If they're not, then you say, well, we didn't really have enough sample size. You're shaking your head no?
There's one at 3.6.
Which one?
Bottom
The
left.
first.
This one or
I don't know which one's which.
Yeah.
It's the first one, yeah.
this one?
Yeah.
So this one was, say it again, 3.6. 2.6. So that expected count is too low. So we would have to say our assumption is not met. 1 out of 8 cells is too small.
How do you do that, how do you check B?
Hopefully not, but what?
How do you check B?
I'll tell you in a second. Okay, that's it. You have homework over 10.5 due tonight. And then this homework over 11.2 is due Wednesday night. And I will get the review sheet for the final posted this afternoon. If you don't see it by this evening, email me because I forgot again. I was going to do it last Friday and nobody emailed me. See, it's your fault.
So if it counts to